Section 7, Physics 122. At the end of Section 6, if we scroll back up here a little bit, we came across the idea of self-induction. After having talked about transformers, among other things, I talked about how, in a transformer, one coil induces a voltage in another coil. It's an example of Faraday's law. And then I said, not only will a coil induce a voltage in some other coil, it will also induce a voltage in itself, because any coil with a changing magnetic flux through it has a voltage induced according to Faraday's law, and that includes the coil that produced the magnetic field in the first place. So continuing to build on that in the opening part of Section 7 here, just follow the cursor. We have a circuit that consists of some voltage source over here, E for EMF, and a coil whose self-inductance is L, and a resistor who R ohms is the resistance of the resistor. And the idea is that originally this switch here was left in position A for a long time. And so a current was established flowing around this loop sort of like that, a current I. And then throwing the switch from A to B removes the battery from the circuit, okay? It's supposed to make contact to point B at the same moment that it stops touching point A, which would be kind of difficult to arrange with some mechanical switch, but you start using transistors instead of just chopping a knife switch, and that would actually be a fairly easy thing to accomplish. So anyway, it's just a little thought experiment anyway. The battery goes away, but there is still a loop for the current to follow. Well, the current doesn't stop flowing instantaneously. There really isn't anything in the natural world that happens truly instantaneously. It takes a while for the current to go away, and we're going to look at what happens during that transient period while the current is dropping off, okay? So basically what happens is energy is being removed from the current as it flows through the resistor, because resistors convert electrical energy into thermal energy. Okay, so the resistor is being heated up, and that takes energy away. Where does the energy come from to continue making the current flow? Well, the magnetic field around this inductor was full of energy, okay? As the field gets weaker, because you see the strength of the magnetic field is proportional to the current. If you go back a week or two and look at the formulas for the magnetic field of a straight wire or a coil or anything like that, the strength of the magnetic field is always proportional to the current. So as you have less and less amps flowing through the wires, you get a weaker and weaker magnetic field around them. Where is the energy from that magnetic field going to as the field decays away? Well, it goes into pushing the current around the circuit. The coil starts acting like a battery in that it produces, batteries get their voltage from chemistry, and this gets its voltage from Faraday's law, so it's a completely different process going on. But as far as the end result on the circuit, it's kind of sort of the same, in that there's a voltage here that keeps pushing the current around. Of course, as the magnetic field gets weaker and weaker, that voltage gets weaker and weaker, and the amount of current sort of tapers off. So let's see, what did I write here anyhow? At t equals 0, the moment you've chosen to start the clock, At t equals 0, the switch is quickly thrown from A to B. What is the current as a function of time? And I kind of said all of this stuff that it says here already. If you work through all the mathematical details, which I won't burden you with, the end result is this exponential function in the box over here, okay? When you draw a picture of it, it looks like this. You have an asymptote over here. As time becomes very large, the curve gets closer and closer to the horizontal axis, but it never quite touches it. So from a mathematician's point of view, the current never reaches 0. From a more practical point of view, yeah, it goes away eventually in the sense that it becomes too small to measure and gets lost in the random thermal motion of the electrons inside the wires. But there is no clear-cut moment when you can say the current stopped flowing then. The current just kind of fades away. So we want some sort of a basis for comparison. If you want to be able to say the current stops flowing in this circuit quicker than it stops flowing in that circuit, well, if you want to have that kind of conversation, you can't just talk about how much time for the current to stop, because that's, like I said, that's fuzzy. It just kind of fades. So to have a more well-defined basis for comparison, instead of the time for the current to stop, how about the time for it to reach 37% of its original value? Why 37%? Well, it's not exactly 37%. It rounds off to 37%, but it's because that particular thing is very easy to calculate. It's just L over R. L is the inductance of the coil, R is the resistance of the resistor. If you wanted to do 50% or 10% or something else, it would be more complicated to calculate. So that's what's done, is to base it on this 37% thing. And that amount of time is called the circuit's time constant, like it says over here. Okay, L over R, time constant. The way I phrased it in the write-up here is to say that's the amount of time to get about 63%, to be precise, 1 minus 1 over E. E is a transcendental number like pi. It goes on and on forever without terminating or repeating. It's used as a base for a natural logarithm. Yeah, you can just think of it as a button on your calculator. We don't need to get too deeply into this. If you ever need to know the value of E to quite a few decimal places, your calculator almost certainly has an E to the X button on it. Just punch up E to the first power and you should see 2.718 and so on. So 63% of the way to the final value. In other words, I said 37% here. 37% left is the same thing as saying 63% of the way down. Still got 37% of the way to go. 63% of it has already gone away, and whichever way you want to look at it. So would be the amount of time when the current is approximately 37% of the original current. The equation of this graph is what's shown in the box over here. I equals the original current, I0 or IO, whatever you want to call that, O for original maybe, and e to the minus t over tau. The Greek letter tau is what's on the bottom. Tau is the time constant, like in the other box. T on top there means what time is it? Where are you along the horizontal axis? So the time constant is a fixed number for a certain circuit. It's L over R. The T above it there is a variable. As the clock runs, T gets bigger and bigger. What if, instead of turning the circuit off, what if you're turning it on? If you originally have a series circuit with a resistor and a coil, and it's not hooked up to anything, hasn't been for a long time, so there's no current flowing, and then you throw a switch and turn it on. Well, that's what's a little further down the page here. And this graph is just the one I was talking about a minute ago, turned upside down, okay? It's the exact same shape. This time it approaches the asymptote from below rather than above. And the asymptote, instead of being at a current of 0, the asymptote is the final current that you approach as the time gets very, very large. And that final current would just simply be what you get from Ohm's law, okay? So if you've thrown the switch back to point A to turn the circuit on, well, the self-induced voltage, that was at the end of section 6. I guess I can scroll back up there for a moment. The self-induced voltage across a coil is the inductance of the coil times the rate the current is changing, delta I over delta T. When you reach a final steady state, the current is not changing. The delta I would be 0. So when you have just steady, unchanging direct current, a coil is just another piece of wire. There is no voltage induced here when it's steady DC. So at that point, all you have is a battery with a resistor across it. So the amount of current that flows would be the current given by Ohm's law, amps equals volts divided by ohms. So that's the final steady state value that the current approaches as time gets very large. Just like before, the time constant, L over R, is how much time to get about 63% of the way from where you started to where you're going to end up. This time that means 63% of the way up instead of 63% of the way down. And so having said all of that, now it's time for me to pick up my piece of chalk and run through this. And after examples for me, problems for you, right? So I'll show you how to do this one. And then after that, we've got one that's kind of similar for you to try your hand at. Or, if you're feeling confident, maybe you should see if you can do this one. The more exercise you get, the better. So I'll leave it up to you. Like I have any control over what you do when you're sitting there in your own home anyhow. But what I had in mind anyhow is that you watch me do this one and then you stop the video and see if you can do this kind of similar one yourself. And then you start it up again to compare to what I did. So we'll stop the screen share and maybe slide this over here. Number 1. First thing it asks for is the time constant. If this pops up on a test, this is not too bad because the question says find the time constant. You look at your formula sheet, it says time constant equals L over R. Well, not too far away, it also says time constant equals R times C. We'll get to that in a minute. But that's for that's for an RC circuit, a circuit with a resistor and a capacitor in it. This circuit doesn't have a capacitor, it has a coil. So you don't want RC, you want L over R, because L is the inductance of a coil. Inductance, 20 millihenries, it's the same story as with many types of calculations. You have to convert into the proper unit. So millihenries to henries, you move the decimal 3 places, 0.02 of a henry. Divide by 5 ohms and 0.004. Put a 0 on the end for another significant figure. That's measured in seconds. Question doesn't specify what unit to express the answer in, so it's fine to leave it like that. Although what many people might do is to call it 4 milliseconds. So that was part A. Part B, the final current as the time becomes very large. Well, this is the whole thing I was talking about a minute ago. As time becomes very large, you approach having steady direct current. If the current is steady, there is no induced voltage, and so it's just a battery with a resistor. You just used Ohm's law. I suppose the phrase steady DC might be a bit redundant. If it wasn't steady, it wouldn't be DC. I mean, you know, it's kind of hard to picture a steady alternating current because alternating current is by definition constantly changing. Anyway, the word steady would have been good enough. No induced voltage, therefore it's just I equals V over R, or E for EMF over R, if you like that notation better. And we've got 12 volts. Oh, wait a minute, I'm looking at the wrong question. We've got 10 volts. Gee, you would almost think somebody might have set this question up for the numbers to work out even. It comes out 2.00 amps. Amperes, if you're feeling formal. What is the current after one time constant? Well, there's actually a couple of ways of figuring this out. There's that equation that's, you know, I as a function of t, you could use that. But I sort of feel right now like emphasizing the basic idea of what the time constant means in the first place. So I'll do it this way. Time constant means time constant means the time needed to reach about 37%, 1 over E to be precise, of the original, in this case, the original current. And so I will just take the answer to part B and multiply it by 1 over E, and that'll be how much current is flowing after one time constant. I'll just slide you a little to the side here. 1 over E times 2 amps. In other words, 2 divided by equals 0.736. Or if you just took the 2 amps and multiplied it by 0.37, well, that would be very slightly off, but not so much that I would take off any points on a test. I'd give you full credit for that. So A, B, C, we must now be to part D. After another time constant, the current will have been reduced by another factor of 1 over E. So the answer to, well, here again, there's a couple of ways you could do it. You could use that function where it's I equals, e to the, well, I equals I0, e to the negative t over tau. You could calculate the answer from that. Or if you want to just focus on the basic idea of what the time constant means, the previous answer, 0.736 of an amp, so what you had at the end of the first 4 milliseconds becomes the original current at the start of the next 4 milliseconds. And so just repeat the same process to find what the current is at the end of that 4 milliseconds. 0.736 divided by E again. And you've got 0.271 of an amp. And in case anybody's starting to lose track, that's the current 8 milliseconds after the switch was thrown. Finally, part E. This time it's not an even number of time constants. So this time you really have to get out the formula and use the e to the x button on your calculator and so forth. Now, one mistake I see fairly often is there's this mistake, this formula for the case where the current is going down, and then there's the other one, which is for when the current is building up. And sometimes when it's a question about one of those things, people grab the formula for the other one. So, read the question carefully and have it clear in your mind what's going on, and read the formula sheet carefully so you don't grab the wrong equation for the wrong situation. Original current, 2 amps, first through the switch. E to the negative, okay, T means what time do you want to know the current? You want to know the current at T equals 6 milliseconds. And the tau underneath it is the time constant, which is 4 milliseconds. Now, as I've probably already said to you quite a few times, when in doubt, convert to standard units. It's not always necessary, but it's never wrong. So if you're feeling a little insecure, 0.006 of a second over 0.004 of a second, that will get you the right answer also. But this is one of those cases where if you keep an eye on what the units are doing, converting to standard units turns out not to be necessary, because you see milliseconds cancels milliseconds. All that matters is that this number is half again as big as that one, okay? It's just a dimensionless ratio. You could have them both in weeks if you wanted to do it in a really unusual way, and it's still going to be the same ratio. You'll still have e to the negative 1.5 power. But when in doubt, convert to standard units. So 2 times e to the negative 1.5. 6 divided by 4 is 1.5. E to the negative 1.5 is about 0.2231. If you're a little bit unfamiliar with how to use the e to the x button on your calculator, you might want to pause here for a moment and make sure you see how to enter that and get this. And the answer is 0.446 of an ampere. And so now I want you to try number 2. If you don't happen to have the printed notes right next to you, maybe I should go back to the screen share for a minute so you can read the question off the screen. That would be this one over here. So I'm gonna, well, you pause it here. I'm just gonna kind of stop talking for 5 or 10 seconds and then go over this. But you should pause and see if you can do this yourself, because, you know, I must have given you this little talk before. It's one thing to watch somebody else do something. It's another thing to be able to do it yourself. You can't learn to swim by sitting on the bleachers watching other people in the pool. It's like, oh, I see, that's easy. You just kick your legs and flap your arms around, and then I throw you in the deep end and you drown. You have to get in it and get the feel for it. And anyhow, I'll stop talking and let you work. Okay. Pretty good about there, I guess. First part asks for the time constant. Just like in that other one over there, L over R. 0.013, 13 millihenries, 0.013 of a henry, and 8 ohms of resistance. Now, realistically, textbook problems quite often have these pure inductances in series with a pure resistance. Yeah, well, you know what? In the real world, wire has resistance. And as a practical matter, that 8 ohms is probably the resistance of the wire that coil is made out of. All you'd have to do is just walk up with a coil and hook it to the battery, and you wouldn't really need a separate resistor if only 8 ohms is what you're talking about. Anyway, you divide and you get 0.001625 of a second, which is a perfectly good way of expressing the answer. Or if you don't like decimal points with zeros, you could call it 1.625, 1 5/8 if I remember my fractions correctly, milliseconds. Part B. What is the final steady state current? Well, just like before, Ohm's law, I equals V over R, or this time maybe I'll call it E over R, because we seem to kind of go back and forth with the notation, don't we? Anyhow, it's a 12-volt battery, and you've got 8 ohms of resistance, 1.50 amps. Part C. Okay, in this case, you've got the thing building up. In number 1, what did I say when I was writing that down? In number 1, it was a circuit being turned off. So V over R, that was the current that you started with. Now I want to back it up and see if I was making any sense when I was talking about it. Well, anyhow, in number 1 over there, V over R was the current that you started with, and it goes down from there when you turn the thing off. Now, volts over ohms is what you're building up toward in the end, okay? So you're 63% of the way there after one time constant. If you want to just think in terms of 63%, that comes out 0.945 of an amp, which is close enough. If you really want to do it nice and accurately, it's actually 0.948 of an amp. Actually be, that's better, because you see, it's not exactly 63%. It just rounds off to 63 for the nearest whole number. So that makes a little bit of difference, but not very much. Like I said earlier, if you gave me this on a test, I'd call it close enough, give you full credit. And then part D. To find the current at any time t, it would be I equals the final current that you're building up toward. Well, I already calculated that back over here. That was the answer to part B, okay? E over R, that's Ohm's law, I equals E over R. So So this factor here is the final current that you approach as time becomes very large. The rest of the formula is 1 minus e to the negative t over tau. And so we've got 1 minus e to the negative 6 milliseconds divided by 1.625 milliseconds. So this part of it right here, that's e to the negative 3.692, which equals 0.0249. You've got 1 minus 0.0249, which comes out 0.9751. So after 6 milliseconds, it's most of the way to its final value. Just got a little ways to go yet. Let's see. Back to the notes, or the note packet. This is all notes. Well, what if instead of a resistor and a coil, what if you had a resistor and a capacitor? It's kind of the same story all over again, which is why I like to talk about these two things together like this. You go into most textbooks and they've got these two topics about 6 chapters apart. They've got RC circuits in the section on capacitors, which is in the part of the book that's about electric fields. And they've got LR circuits in the part of the book that's about magnetic fields. But they behave in exactly the same way. What I'm about to say here is pretty much a rerun of what I just went through, just with a few words, you know, cross out the word inductor, put the word capacitor instead. The way that an inductor stores energy in its magnetic field is kind of the same general sort of thing for how a capacitor stores energy in its electric field, the electric field between the plates of the capacitor. So you get exactly the same exponential function describing what's going on. So we start out here with a capacitor which was originally charged up to some charge Q0. And when charged up like that, there is some original voltage V0, or delta V0 to be precise, if you want to be careful about your notation. That would be the voltage between its plates. And so, you know, you previously came along with a battery and some jumper cables and got the capacitor all charged up. And then you take the battery away, and you sit there for a moment and look at it, and then you reach over and you close the switch. Well, once again, nothing happens instantaneously. I mean, what happens eventually is that you know, there's plus charges all over one plate of the capacitor, and there's minus charges all over the other plate of the capacitor. And when you close the switch, you provide a path for them to get together. You know, it's kind of like teenage boys and girls. Anyway, we probably shouldn't get into that. But if you allow them to get together, they seem to be attracted to each other. So a current flows as the plus and minuses try to get together, and it discharges the capacitor, but it doesn't discharge instantaneously. It takes time. And so the charge on the capacitor tapers off exponentially. It's an e to the minus x kind of thing. And this is the exact same graph that was on the previous page, except the vertical axis is labeled with a Q instead of an I. We're talking about the charge on the capacitor instead of the current flowing through a coil. Once again, how long it takes to discharge the thing is described with a time constant. If you ask the question, how long does it take the capacitor to discharge? That's not a very good question, because taken literally, the answer is always forever. But how long does it take to get down to 37% of the original charge? That's a question that you can give a very clearly defined answer to. That amount of time is equal to R times C. What if it's not the charge on the capacitor you care about? What if it's the voltage between the plates? Well, then you just have to go back to the definition of capacitance. Here, wait a second. Capacitance means charge stored per volt. Or actually, I guess that would be delta V if you're really being particular about your notation. I suppose I probably should be. Anyhow, definition of capacitance, which you can look up on the formula sheet a few weeks earlier in the course from where we are now. If you multiply both sides by delta V, it cancels from there, and you've got delta V times C equals Q, and then you divide both sides by C, and so the voltage across a capacitor is equal to the charge. You've got plus Q on one plate and minus Q on the other plate. That's what Q is. And Q divided by C is the voltage. So back to what it says in the notes. Delta V equals Q over C from the definition of capacitance. So you can put the two formulas together. Now now I'm just going to end up wanting to go back to the blackboard again. Let me erase this and make a little more space. So as far as what's on the formula sheet, you have to take two different things and put them together, okay? You've got this formula for the charge, and you've got this thing here that comes from the definition of capacitance. So as with a lot of times, I'm going to make you think about things a little bit and say, oh, I can put this together with that, and that's what would give me what I needed. Now, you could just calculate a number for Q and then divide it by the capacitance, and that would get you where you wanted to go. But as sometimes is the case, it might simplify things a little bit if you do the algebra first before you put the numbers in. Let me demonstrate. Back to the, oh, where did the, it's up here, isn't it? So you've got delta V equals Q over C. Well, you've got this formula for Q, which is, let's see, that was the one for when it's discharging. That was, I got to look at it. I forgot my hard copy of the thing. Yeah, Q0 e to the minus, right? So Q equals Q0 e to the minus T over tau. And then you see if delta V is equal to Q over C, like I said back over there, I suppose I could get them both on the screen at the same time, kind of like that. So if delta V is equal to Q over C, well, then the original voltage would equal the original charge divided by the capacitance, which is what we've got there. So the moral of the story is delta V equals delta V original e to the minus T over tau. So if it was me, I would probably derive the formula first from the pieces available on your formula sheet and then stick the numbers into it. That might work a little quicker and slicker than doing it the other way around. Anyway, back to that. So if you need the voltage, you make that substitution, and then what if you have a question that asks about the current? Well, once you have the voltage, current comes from Ohm's law. So you could take that formula that I just wrote on the blackboard there behind me, and you put an R underneath that, and you know, I equals V over R. That would give you a formula for the current. If the capacitor is being charged instead of discharged, I didn't even bother to draw another graph. It would look just like the one on the previous page for the LR circuits, but it's this shape here, flipped upside down again, where it approaches the asymptote from below rather than from above. The final full charge on the capacitor would be capacitance times the EMF of the And again, if you want an expression for voltage as a function of time rather than charge as a function of time, then you would just take this one, and if you notice that if you take this formula and you stick a C underneath it, because volts equals charge divided by C, notice that C over C, you've got this C right here in this formula, and when you divide it by C, there's going to be this one underneath of it, and they just cancel out. So you'd have voltage equals EMF times the thing in parentheses. And again, Ohm's law, actually together with the loop rule, to get the current. So we have a couple more for you to work on. And so you should pause it here, and then I'll run through these, and you can play them one at a time. You know, you can do number 3 and watch me do number 3. Well, anyhow, go ahead. Number 3, they all seem to start out this way, don't they? Except I don't think the next one does. But this one, like number 1 and number 2, starts out asking you for the time constant. Well, when you're dealing with a capacitor instead of a coil, the time constant is RC. And you have both those numbers. Got a lot of resistance. Mega ohm, 1 times 10 to the 6th. 10 microfarad capacitor. Micro means 10 to the negative 6. So you've got a 10-second time constant. That's a long time constant. They're usually in the milliseconds or even shorter than that. But what's going on here is that, you know, 1,000,000 ohms, that's significant. And so the large resistance keeps the current down to something in, you know, in the microamps somewhere. And with such a small amount of current, charge just trickles out of the capacitor a little bit at a time, and it takes a long time for the capacitor to discharge with so much resistance in the way. If the resistance was a lot smaller, then the charge would flow faster. In other words, you'd have a bigger current, and the time constant would be a shorter amount of time. For the second part, it asks for the voltage at a particular time. Well, that was this right up here, okay? What I was talking about just before we broke to let you work on the sample problem. So we've got that voltage. Well, yeah, you can see what I'm doing. I'll just stick the numbers in it. V0 e to the negative t over tau. The original voltage, 500 volts. Okay, so I'm using this one right here. I put in 500 volts for the original voltage, V0, times e to the negative 35 seconds for the time t, 10 seconds for the time constant. Time to move the camera. So we've got 500 e to the negative 3.5 power. The exponential by itself is 0.0302. If you've been having any trouble getting the right answer, that's what you should have gotten for that part of it. You multiply that by the 500 volts. That should give you 15.1. So after 3.5 time constants, there's still 15 volts on this thing. I suppose something I could just throw in here as a little footnote that, you know, capacitors in some situations can hold high voltages like this. Some capacitors are not designed for high voltages, but some of them are. And so, for example, if you're the kind of person who likes to tinker around inside of things, I have heard you should be very careful about microwave ovens because you can get a very dangerous shock even with the thing unplugged, because there's apparently some big capacitors in there that are just kind of waiting to, like, you know, like a snake hiding in the long grass, waiting to jump out and get you. Well, let's see, I did part A, I did part B. It's probably a good idea if I do part C also. So maybe I'll just make a little sketch to kind of illustrate what's going on. We have a circuit that consists of just the capacitor and the resistor. And at this particular moment, there is what I calculated in part B, there's 15.1 volts across that capacitor. It's gonna, at that particular moment, it's gonna act just as if there was a 15.1 volt battery in that spot. I mean, you know, volts is volts, no matter what's making it. So as that capacitor discharges, it'll be pushing a current I around the circuit like that. There's the resistor. And this is just your basic Ohm's law problem. I equals volts over resistance. .51 negative fifth power, measured in amps. 15.1 microamps if you don't like scientific notation. So as I sit down again at my trusty computer monitor, there it is. Let's screen share again. Well, let's see. We've done RC circuits and we've done LR circuits. I wonder, what other way is there of combining these things two at a time? I know, we could have an LC circuit. This is different, okay? RC circuits and LR circuits, like I said before, they behave just exactly the same way. What the coil does with its magnetic field, a capacitor does with its electric field. They both push a current through a resistor that behaves in the same way. A capacitor and an inductor with no resistance is an entirely different story. This circuit oscillates instead of giving you an exponential decay kind of behavior. So let's start out in the first picture here. Follow the little arrow. The capacitor starts out charged. So previously, somebody came along with a battery and some jumper cables, and they connected it to the capacitor for a little while, and they got the top plate charged up positive and the bottom plate charged negative. And then at t equals 0, you close the switch. There's the switch up there. Arrow makes it look like it's just been moved. So, like I was talking about a few minutes ago, pluses and minuses want to get together with each other. And so current begins to flow from the one plate of the capacitor to the other. The magnetic field of a coil is proportional to the number of amps flowing through it. The more amps, the stronger the magnetic field around it. So as the current coming out of the capacitor builds up, the strength of the magnetic field builds up. And fields contain energy. As the capacitor discharges, its electric field gets weaker and weaker. Where is the energy going that was stored in that field? Well, over here, as the current builds up, the magnetic field of the coil is getting stronger and stronger. So the energy that used to be stored in the electric field over here is now stored in the magnetic field over here. So step one, you close the switch, the capacitor starts discharging. Well, when we get to the picture number 2, the capacitor is now completely discharged. Notice that I no longer put a bunch of plus and minus signs all over its plates. But the current doesn't stop because the magnetic field of the coil has energy stored in it, and the coil, in a sense, starts acting like a battery. Okay, the energy stored in that magnetic field has to go somewhere. If the current stopped flowing, there would be no magnetic field, because magnetic fields are found around currents. So as the current starts to drop off, the energy that had been stored in that magnetic field is used to keep the current going long enough to recharge the capacitor. In picture number 3, the current has finally stopped flowing, but now the capacitor is charged up again, the other way around, positive on the bottom this time. So the energy that started out in the electric field gets transferred into the magnetic field of the coil, and as the magnetic field collapses, as the current goes away, the energy gets moved back into the electric field of the capacitor. Well, now here in picture number 3, we're kind of in the same situation we were in picture number 1, except the picture's been turned upside down, but those pluses and minuses still want to get together. And so the current starts to flow back again. The charges are like, well, it didn't work the first time. Let me try again. And so the electrons that are up here, if you want to think in terms of electron flow instead of conventional current, the electrons start heading for that positively charged plate again. And so the electric field gets weaker as the charge leaves and the magnetic field builds up, but then the magnetic field makes it overshoot, and that, here's the current flowing back to recharge the capacitor, which returns us to picture number 1, and the process repeats over and over and over again. And if you had truly resistanceless wires, that there's no reason, like not even a trace of an ohm anywhere in the circuit, the oscillations in principle could continue forever. They might eventually give off some radio waves that would eventually take the energy away from the circuit, but anyway, continue for a long time. If it was, electrical resistance is to an electrical system what friction is to a mechanical system. It takes energy away from the system and converts it into heat, okay? So if you have a few ohms worth of resistance in this thing, the oscillations will stop much sooner because the resistance will take the energy out of the system. So, like it says down here, this circuit, this LC circuit, is the electrical counterpart to a mass bouncing back and forth on a spring, which is something we'll get to in a couple of weeks. Actually, that's briefly mentioned at least in section 9. But the electrons vibrating back and forth inside the wires of that LC circuit have a lot in common with a mass vibrating back and forth on the end of a spring. So the charge on the capacitor is described by this graph over here. It starts out charged up in picture number 1. In picture number 2, the charge is 0. Here would be picture number 3, where the capacitor has been recharged the other way around. And then, the thing just continues on and on like that indefinitely. The equation of that graph is what's written in the box here. It's basically a cosine wave, like right straight out of a math book, where the cosine has been multiplied. See, the biggest that a cosine ever gets is 1. Cosine goes back and forth between plus and minus 1 as you work your way along the graph. If you want the charge to go back and forth between Q max and negative Q max, well, take this number that stands for the maximum charge on the capacitor, the charge it has when it's fully charged. You multiply that by the thing that goes back and forth between 1 and negative 1, and that gives you a charge that goes back and forth between Q and negative Q. Yeah, this is important. This formula has been written assuming that the thing in parentheses is in radians, not degrees. Anytime this comes up on a test, there's always somebody who forgets to convert degrees into radian. Well, you should have your calculator in radian mode. You don't have to convert anything. There's a button you need to find to get it in radian mode instead of having it in degree mode. And some people don't bother to do that, and they end up with some red marks on their paper that way. So remember, this equation requires that you use radians. This thing here that looks like the letter W is actually the Greek letter omega. Let's start over here on the graph to explain what omega is. The time for one complete vibration, whether it's charges inside of a wire going all the way over and then coming all the way back, or whether it's a mass on the end of a spring going all the way one way and all the way back again, that time for one complete vibration is called the period. And that amount of time is represented with a capital T. So I wrote that right here. T, the period, is the time for one complete vibration. And all of this terminology will pop up again. Well, actually, we'll continue to use it on through section 8, and it'll pop up again in section 9 when I'm talking about mechanical vibrations, mass on a spring. Frequency tells you the same thing that the period does, just the other way around. Period is how many seconds for one complete cycle. The frequency is how many cycles per second. Well, seconds per cycle, cycles per second, these things would be each other's reciprocals by definition. F equals 1 over T, or T equals 1 over F. The unit that frequency is measured in, cycles per second, is given a name of its own. It's named after Heinrich Hertz, who discovered radio waves about 150 years ago. Now, this thing omega that appeared back up in here, that's the frequency, basically. This is the only place in the whole physics book that I can think of where they use a different letter for the same thing depending on what unit it's measured in. If you're talking about somebody's height, maybe you're using the letter H for how tall somebody is. If the height is measured in centimeters or the height is measured in inches, you still use H for height. V for velocity, whether it's in feet per second or meters per second. But for some reason, when the frequency is in cycles per second, you call it F. But if you measure it in radians per second, they use omega rather than F, even though it's the same thing, just measured in a different unit. 2 pi radians per cycle, omega equals 2 pi F. Okay, so that's what's sitting in the formula here, is the frequency in radians per second. Radians per second times seconds gives you radians, which is the reason that you need your calculator in radian mode when you use that formula. Phi, the Greek letter phi on the end over here, like I wrote down here. Let's not worry about that too much. It's called the phase angle. If you just remember to start the clock when the capacitor is fully charged, then the phase angle is 0. It'll go away, and I don't really need to say anything else about it at this time. It'll become more of a story when we get into Unit 8. Anyway, what does the frequency of an LC circuit depend on? Well, not too surprisingly, it depends on L and C. You change the capacitance, or if you change the inductance, it'll change the rate at which the charges shake back and forth, or flow back and forth, if you'd rather phrase it that way. The exact relationship turns out to be what's in this box here, 1 over the square root of LC. So that kind of explains what's going on in that circuit. All that's left of Unit 7 is one more problem for you to work on. So you've got this capacitor that's originally charged to 500 volts. And then at t equals 0, you hook it up to this 7.5 millihenry coil. We want to find the period. I'll give you some hints here. You're told L and C, so you can get omega, the so-called angular frequency, the frequency in cycles per second, or radians per second. From omega, you can get F. From F, you can get the period. So that's kind of the plan of attack for part A. You get the period, and then for the voltage after a certain amount of time, this up here will give you the charge after a certain amount of time. To get the voltage, you'll have to divide by the capacitance, as we already did before in one of these other sample problems. So while I'm erasing the blackboard and making some space to write, you can work on the problem and pause it while I'm doing that, and then I'll go over it with you. Doing a good job erasing a chalkboard is kind of like doing a good job painting a wall, okay? You're painting a wall, you run the roller up and down this way, but then when you're done, go back and forth the other way to get, smooth it out a little more. Yeah, that looks pretty good. Number 5. Part A. Well, I already kind of summarized this for you while we were still looking at the printed notes. To get the so-called angular frequency, the frequency in radians per second, 1 over the square root of LC. Of course, as usual, you have to fix the units. 7.5 millihenries, that's 7.5 10 to the negative third of a henry. I don't have quite enough space for the capacitance there, do I? Ten microfarads would be 10 times 10 to the negative 6. In other words, 1 times 10 to the negative 5th. Although, if it's easier for you, the calculator should accept it as 10 times 10 to the negative 6. If you'd rather do it that way, I'm pretty sure it'll work. That comes out 3651 radians per second. I'll round it off a little better when we get to the answer, but I always kind of like to carry an extra decimal place through the intermediate steps. omega equals 2 pi f, that implies f equals omega over 2 pi. Omega is that number right there. I don't know if I need to write it down again. You take 3651, you divide it by 2 pi. You know, people get caught by that all the time. They punch in, you got your calculator, 3651 divided by 2 times pi. And they get an answer that's roughly 10 times as big as it should be, because pi squared is roughly 10. Not exactly, but roughly. You have to go 3651 divided by 2 divided by pi. Otherwise, you end up with, your calculator interprets it like that. If you put 3651 divided by 2 times pi, it's gonna do that. It's gonna multiply where you wanted it to divide. So either divided by 2 divided by pi, or if it makes more sense to you to do it this way, put parentheses around the 2 pi, and then it'll be dividing by the whole thing instead of just the first thing that it encounters. Sort of a little order of operations thing that, I don't even know if it's an order of operations thing, but it's something that I see people get caught by all the time. Anyhow, assuming you entered the appropriate keystrokes, that should have come out 581. I guess the other way of getting around it is you could just put in 6.28 and not worry about parentheses or anything like that. 2 pi is about 6.28, close enough. That's the frequency. What the question asked for was the period. (0.00172 of a sec). Wait a minute. No. I should read my own notes. I'm going to the trouble of holding on to them. That's what you get after you divide. Guess I must have zoned out for a moment there. 581, or 1 divided by 581. Okay, I got the frequency here. 1 divided by 581 is this number here, and that's the answer. And so I should put a box around it. And there is a part B. It wants the voltage at some particular time. So what's available on the formula sheet is charge as a function of time. It's the same trick that we used once or twice in some of these other examples. If C is equal to Q over V, that implies that V equals Q over C. So the voltage would be, well, we have a formula that's equal to Q. Put the formula for Q where the Q was. That's Q max cosine of omega t phase angle phi. Since Q over C equals volts, Q max over C would be the maximum volts, which was the 500. And I determined, does that still show up? I can lean it over to the side a little more like that. We determined back up here that omega was 3651. So that's what'll go in there. And if you start the clock when the voltage and charge are at their maximum, it just makes the phase angle equal to 0. So the voltage as a function of time, maybe I'll write it out before I stick in the specific time. That's the voltage as a function of time for this particular circuit. $36.51 is in radians per second. Time is 0.0015 of a second. So see, seconds cancel seconds, and you're left with the cosine of a certain number of radians. I almost fit that in there, but I need a little more space. And if you had your calculator in the correct mode and otherwise pushed the correct buttons, the cosine of 5.48 radians should have come out approximately, rounding it off a little, 0.692, which means the answer comes out 346 volts. And I believe this is where I click stop.